Do you need me all to pull up the, no? Oh, it's technology. If anyone has any, I'll just leave this up for a couple minutes. Anyone just online? Okay, I'm not sharing. I'll just give it a couple minutes for everyone online to, check in. Cool. All right. All right, so I'm actually feeling pretty energetic, so. Um, So why don't we get started right now? So this is the Machine Learning 103 notebook that we're going to be working with tonight. As always, first, everyone's just going to make their own copy. So we're not going to work with it. So this is the Machine Learning 103 notebook. So the first things I'm going to talk about are the functions I'm importing. So I'm not going to cover NumPy, Pandas, and Matplotlib, because we covered in the last two. But the two important ones you need to know for tonight are PyTorch and Torch Engine. PyTorch is the library to write neural network code in. It's very useful. It gives you a lot of control on how you write your code. Like it tells you basically can architecture your neural network exactly how you want it, how you want to train it, how you want to feed the data in. It gives you a lot of control. The downside is it gives you a lot of control. In a sort of really bad analogy, you can think of PyTorch as the C++ of neural network libraries. It gives you all the controls, and then it also gives you all the controls so you can shoot yourself in the foot. There's another popular library out there that you may have heard of called TensorFlow. It comes from Google. TensorFlow is also really popular. It's less oriented towards giving you that control and more about quickly developing a model and like employing it into enterprise and production. PyTorch is much more popular in research, which is where you're going to find all the really good models. And it's just I'm biased because I am a researcher when I say I think it's better, but basically it's just one of two options. You'll also see some other libraries out there or some other languages, like maybe Julia, or R you might see there. I'm not super familiar with either of those. Python is where it's mostly at, but they work in the same way, just syntax mostly. So PyTorch is imported using the torch name. And there's a few different functions we need to look at here. Basically, the four important ones we need to talk about are first, NN. NN is basically the layers of the neural network. So if you saw before, I'll pull a picture. a neural network is divided by like a number of lines, right? These lines that we call here, we call them layers. And like this model would have 3 layers. We would have a first hidden layer, a second hidden layer, and an output. And so these were what we would call linear layers, because they're just like linear multiplications. They're basically what I talked about before, just pass in, pass out. And those and other types of layers are controlled in the NN library, which is just neural network. Next is NN.functional, which we're going to call F. This controls all the activation functions. This is the ReLU, this is the sigmoid, this is the leaky ReLU, this is the tanh. Next is the data loader here. What the data loader is going to do, it basically lets us control how much data, basically controls how we're going to feed the data into the neural network. And it's just it's a very convenient piece of code to sort of separate out the data into much more easy to manage chunks, which I'll get into why that's important later. And then finally here is Optum, which Optum is our optimizer. Now, I know I didn't address what optimizers are in the presentation. And basically optimizers are how we control the gradient descent when we go down the loss curve. There's a bunch of different ways to do it. Tonight I'll be covering the simplest version, which is known as stochastic gradient descent. And you can just import that with Optum. And then finally, there's a helper library here called TorchVision. This is basically just a additional library PyTorch provides that lets you gives you some convenient controls over PyTorch, specifically with images. The first one here is datasets. This is basically just this is just a sub-library that lets you easily import datasets from import existing datasets. Like tonight, we're going to be working with MNIST, which is like a handwritten digit classification data set, and that's what we're going to be using it for. And then we have here transforms, which basically just do transformations or transformations on the images. Like we could correct the color, we could crop them somehow, we can mess with the colors, things like that. So as always, we first just run this cell. Make sure. Up here. And now I can change that. Give me one second. It's telling me I have usage limits. I disagree. So we're going to do something funny in a second, and we're going to watch it. I switch to a different account. I would say don't see my password, but you can't see my password. Apologies for this. I can't. So the reason why I'm taking this step, by the way, is basically, as I will get into a minute, you want to be using a GPU. GPUs make doing machine learning from a really slow and impossible process to a really fast and very convenient process. That's not true. Sorry, I was saying that's not true to it blocking you, not. I'm sorry, there we go. Take a copy and die. Now, if anyone else did anyone else get the GPU error, or was that just me? Was that just me? So yeah, but anyway, we're going to first run this cell, and this basically just imports everything we need into our environment. And it's very easy. So once we're going to let that finish running, as you can see the little green arrow, it's telling us each line of code running. Nice. And now it's running. Yeah.
Just a quick question, like with you changing it to GPU, is there still a CPU in there that's like,
yes,
doing small?
Yeah, there's basically I will get into it, but basically the GPU will do the model code. Yeah. Like when you have the neural network will be loaded onto the GPU, the data being captured will be done on the GPU, but everything else will be done on the CPU.
Yeah, no, I was just wondering if like the GPU was doing everything.
Oh, no.
It makes sense.
No. So, yeah, no, so actually, I will get into that. So first, next thing we're going to do is we're going to check for CUDA. What CUDA, also known as the Compute Unified Device Architecture, it's like a special platform that NVIDIA has developed that lets you do parallel processing on GPUs. And specifically, it does the sort of matrix multiplication processes very, very easy, because GPUs were originally designed for graphics, and graphics are actually quite similar to neural networks in the sense that they primarily work with a lot of matrices. So instead of having to use it to generate graphics, we use it to calculate neural networks. And so because GPUs are specifically designed for matrix multiplication, they make doing neural networks and training them really, really, really fast. So if you can, and let me phrase, unless you are in some unbelievably extenuating circumstances where I can't even imagine why you're in them, get a GPU and train on those. Because otherwise you're going to spend time forever. So basically here, we're going to first just check if we can access CUDA. We can, all right? We have a GPU. And so here, we're just basically setting what device we're going to use. And we're just saying, we're going to use the CUDA device, which is just our GPU. Right? Cool. So we've imported, we've made sure we can use our GPU. We're going to get into our data set now. So tonight, we're going to be working with the MNIST data set. The MNIST data set is a very popular and kind of old data set, specifically about doing digit classification. And as you can see here, it's basically 70,000 black and white images of handwritten digits and a bunch of different styles. And each digit is given a classification of what numbers on it. And what we're going to be doing tonight, we're going to be training a neural network that's going to be able to learn how to classify the digit based on the image. So first, we need to grab the data sets we need to first grab our data set. And so for that, we're going to write some very simple, easy lines. We're going to do datasets.mnist. And so we're going to specify a few things. First is root. And root is just going to be where it's saved. And then train, this will tell us if we're grabbing the training set or the testing set. So we're going to grab the training set first. So we want it to be trained with true. Next, we want it to download. This will just make sure we actually download it from the web. Download true. And then transform is basically how we're going to transform the data right after. And all we need to do here is toTensor. And the reason why we run toTensor is that when we originally download the data, it's going to be in NumPy arrays, but PyTorch really would rather prefer to work in tensors, which are really similar to NumPy arrays, but they are more optimized for machine learning tasks internally. So we're just doing the conversion. Anyone have any questions so far? Cool. Then we're going to do a similar import of just.mnist with those data. And this time it's false because it's our testing data. And do download is true. And transform false to tensor. And so we're going to now simply run this out. And so now what's going on here is that we are downloading our data sets. Why is it yelling at me? Oh, I made a typo. That's really annoying. Cool. All right, next. So now that we've downloaded it, we're just going to get a quick sort of visual of what our data looks like. I have some example visualization code here. I'm not going to get into how this works tonight, but if you are curious, just message me or someone else on the Discord server, and I can help explain what's going on. But as you can see here, this code, we kind of get just a basic visualization of what our data is looking like. I'm actually going to zoom in so we can see better. So as you can see, every number has a ground truth and is written basically as a black and white image, right? And sort of like, this is a 5, this is a 0, this is a 9, this is a 2. Big, it's something like that.
North is a five.
But
Is the handwritten digits. The thing we need to know though, very importantly, is that they are very specifically 28 by 28 pixels. This is very important because this is going to be important when we feed into the neural network. So we need to feed it in exactly so that every pixel in this image can go has a input. So the one 28 by 28, by the way, is 784. Remember this number. This will be useful. So next, so cool. We have our input data. We know it's basically a series of images of 784 pixels. What we need to do now is we need to make our PyTorch model. We need to design the architecture for our neural network. And so tonight we're going to make a very simple model. It's basically just going to be, it's going to basically be 3 layers. We're going to pass 780, we're going to pass the image in to a hidden layer of 512 neurons, then to another layer of 512 neurons, and then finally 1 to 10 neurons. And the way basically this is going to look, I can cover that. Basically, we're going to take our image
like this. We're going to take each pixel and then spread it out into a sort of just chain of pixels, 784 pixels long. And then we're first going to pass this into a layer of 512 neurons. I am not an art major, by the way.
Is there a reason why we chose 512 neurons?
Great question. The answer is there's not a specific reason. So I will answer it in 2 ways. There is and isn't a specific reason. The reason why we chose 512 is just a sort of guesstimate on what a good number of neurons in the hidden layer will be to learn the data. It's actually, there's no great science to figuring out how many neurons there need to be in the hidden layer. It's actually there's something called neural architecture search, which is basically an entire subfield of doing automated searches for finding the best architectures for neural networks for a problem. And it's kind of arbitrary, but the reason why we chose, but there is something to note in that most neural layers are operated by multiples of 2. I've not seen a reason why it's multiples of 2 other than it's good practice. You can technically do it with how many neurons you want, but it's generally encouraged to operate in multiples of 2. Oh yeah, probably. That would make sense. Probably with memory. Yeah. So then we're going to pass it to another 512 layer. And then we're going to pass that second 512 layer into one of 10. This is a very simple network. And then obviously we have 10 because there's 10 digits out there. So this is the network we're going to be designing tonight. So with PyTorch, there are basically 2 functions we ever really care about. There's more that you can do if you're designing fancy stuff, but there's basically 2: init and forward. What init does is basically init is where we define our layers. Like we're going to find each of those layers I drew there, and we're going to define. We're going to find that's what we're going to find the layers. I was about to say we're going to find the explanation of it. So first, here we're going to need to do 2 things. We first need to define how we're going to flatten it. Like as you saw before, we can't feed in an image itself. We need to stretch it into a long line. And so for that, we're going to call it self.flatten equals neural network.flatten. There's it. And then after that, we're going to have our linear layers. Does anyone have any questions so far before we get to that? No? Cool. Right. So I'm just going to pull this to the side as our example. So as I showed before, we're basically going to have 3 layers. a 784 to 512, a 512 to 512, and a 10. And to write these linear layers is very simple. We're gonna do first FC1, and it will be dot NN dot linear of 784 to 512. And that's it. Now we're going to do a second one. And then dot linear. 512 to dot 12. And then we're going to do our FC output of and then dot linear in 512 together. Make sense? Yeah. I made a typo again. Don't be like me. I don't make typos. Okay, cool. This makes sense, right? Very simple architecture. I'll even give you all a minute to write the code. Cool. Right, so next we need to write the forward passing. And what we basically need to do is we need to pass X through the flatten, and then through FC1, and through FC2, then through FC output. And that'll basically just be the order that we should here. This will be flatten. This is FC1, this is FC2, and then this is FC out. So first, what we need to do is that it's very simple. We're basically just going to call self.flatten X for the flattening. And then next, I'm going from 784 to 512. As simple as SFF equals FC1X. And then similarly, what we're doing 512 to 512, and FC2X. And from 512 to 10, let me add that FC output. X. Then we go from return. And this is our neural network. We have just passed all our input through all the layers. Congratulations, you just wrote a neural network. Very simple. PyTorch makes it really easy to just write a neural network, just like this. Now, I'll give you all a minute to write it down. And then once we've written this, just run the cell. And so this is design. And next, we're just going to create a neural network instance. One thing you will note here is this really right correction there. So one thing we need to see here is our neural network. And so what here is model.2. So if you remember, all the way at the top, we did this device, and we basically were checking, can we access the GPU or not? This is when it becomes important. What we're basically doing here is that we're purposely sending the model from the CPU, and we're loading it onto the GPU. And so this will be here for our model, and then when we're passing in data through our model, we have to upload it to the GPU first, but we're using something similar. So we're going to run the cell, and this is our neural network. And as you can see, all of our layers that we showed before are in the network. Very simple. Okay. So next is our training loop. So the training loop is generally quite the same process. It basically, we're going to feed in the model, but we're basically going to do a few things. One, we're going to compute the prediction. We're going to feed in our input and compute the predictions, and then find how wrong we were, our loss, and then we're going to backpropagate it. And so for that, here you're seeing a bunch of extra code I have here. To explain this is first doing model.train. This is setting our neural network into a training mode. And for tonight, this is actually not important. But whenever you're working with other fancy techniques, such like batch normalization or dropout, which if you're curious about, just ask me afterward, I'll explain it. But it's not really necessary, but it's always good practice to have. And then here is us iterating through the batches. And I know I haven't covered batches yet, but think of batches as like small handfuls of the data that we're passing through to have the model just learn on that in that instance. And we mainly do it because GPUs have limited memory. Like the 3070 has 8 gigabytes, and if we had 1 million images, we couldn't load them all onto the GPU. So we have to send batches of the data to the GPU and then process, and then figure out the loss and backpropagation of that. So that's what this is for. So first, for computing the prediction and loss, since we have our input and our output, our x and y, we're going to first just do the same thing as before of x dot to device and y dot to device. So now the model and the data are both on the GPU. And so using, so then just to show up, if you remember, we created a model, instance. We're going to just do predictions. And to get our predictions, we're going to pass our input through the model. And this will automatically call forward. It'll call the forward function and pass it through automatically. And then for our loss, we're going to use our input here of our loss function, which I will get into what we're going to use later. But this will also be as simple as the input of our predictions and then the ground truth y. So now we have our loss. Great. And this is step 2. This was step 1, and then this was step 2. So now we're going to get into the backpropagation, which is steps 3 and 4. So first, we have to run a piece of code called optimizer.zeroGrad. And basically, this just resets the gradients in the optimizer. And you always need to run this so that you're not like having the, if you don't reset the gradients each time, your network will train incorrectly and it'll actually perform really poorly. So next is when we reset it. Now next we just call loss.backwards. And this actually finds the gradient. Like when this helps through backpropagation to find the gradients themselves. And then finally we're going to do optimizer.step. Next, now that we have the batch size. Okay, now, so this is also some printing metrics. I won't cover these. If you want, you can always just copy paste. Basically, what this does is that it's going to check if the current batch is a multiple of 100. Basically, if the data contains one of the multiple of 100, and then it's just going to grab the current loss and just print it out. So this is the training. And so like before, this is like the step 1, step 2. We're going to get our loss, then we figure out how we need to update the weight, and we update it. And we're going to do this over all of our data. And we're going to run this train loop multiple times, as we'll see later. But we also can set up our testing loop. And the testing loop is similar, but different. So instead of calling the model.train, we're going to call model.eval. And this just sets it into an evaluation. For the same reason that before with the sort of techniques we use in training, like sometimes you want to turn them on and off, not perform the night, but good practice. Then this is just some statistical information on how much data we're throwing in and the number of batches we're going to move through. But what we really need to do is write these two things: test loss equals 0 and correct equals 0. And so these are going to be our testing metrics to see how well our models are. And so testing loss is basically just the loss function value. And correct will be used for accuracy, which will be just literally how many times are we correctly getting it. And so for creating the testing loop, it's very simple, same as before, we're gonna send our data to the GPU. And then to calculate the loss, and model X. And then we're going to get a loss, going to be loss function. Right, Y. And then we're going to add our loss to our test loss. An item here just like extracts out the value itself. Whoops. Equals. And then next, we're going to add the correct. And so here we're going to do a couple things. First, we're going to do credit.argmax. And this is basically just going to check from the output values, which one has the largest value and what is the index of the of that value in the array. This basically just gets, and what this does is that this is going to get us the found class of the prediction. This is basically how we're going to figure out if the model said 0, 1, 2, et cetera, et cetera. And then we're going to check to see if it actually got the correct prediction. And then we're going to write some, and since we are dealing with a batch size here, we need to first convert these to floats. And then we're going to sum them up. Like if we passed in 8 images and 3 of them were correct, basically this function here would look like 0, 0, 1, 0, 0, 1, 0. Like this would be here. And so when we sum it, we're just going to get basically the number of correct. And we're going to call it. So once we do that and we get our loss, basically we're then going to just average things out. Let's do test loss right equal the batches. And then correct right equal. Anyone have any questions? Okay. Cool. So we're going to run the Selman and complete it for me. And so next we have to get into, now that we have our model and our training loop, we now have to set up all of our hyperparameters for our training. And for tonight, hyperparameters are basically going to be how we control how the model changes. Train. So there are 3 hyperparameters we need to care about tonight. First is epochs. Epochs is basically the number of times we go through the training. In other words, how many times we're going to call this. Like if I set the epochs to 10, we're going to call a training loop 10 times. Very simple. Next is the learning rate. If you remember before, the learning rate basically just controls how quickly we descend down the loss function. If we set it too small, we're going to take forever to convert. We're going to take forever to find the smallest value. But if we set it too high, we're going to basically just jump all across the curve of that loss function everywhere, and not actually probably reach a small value. And then finally, batch size basically just controls how much data in like a small batch we load onto the GPU for that moment. And this is done because of GPU memory constraints. You would think generally you want to feed in as much data as possible, but I have found in practical purposes that is not always true. Because that's one thing, when you feed more data, when you take a larger batch, you're going to run that training loop fewer times. You're going to like update the weights fewer times. So if you increase your batch size, you have to actually train for a longer amount of time. Or you have to update the learning rate to go more quickly. because you now are like just using more data and therefore running it less often. But as we talked about before, updating the learning rate can cause the jumping around. So this is my opinion, this isn't always considered best practice. Sometimes it's better to have a slightly smaller batch size, but generally you do want to have as much data as you can fit in. Because as you have a larger batch size, the sort of gradient you compute based off of your loss will be more accurate. Like if you compute one, who knows where that one is going? But if you have 64, like data points that all have a direct link that you need to go, like going down the loss, it's gonna be more accurate. So those are our three hyperparameters. Next, we need to control like what our loss function is going to be. So our loss function for tonight is going to be cross entropy. And cross entropy is basically a classification, basically a classification loss function that basically punishes the model for being incorrect with its how much it thinks it will punish the model for thinking, hey, this class is very likely, and punishing the model for being unsure. Like, for example, here, as you can see, for the dog, the prediction thinks it's one of these two classes, and it's really this one, and it's quite unsure on either of them, so it punishes really high. But if you look here, if you look at the sort of probabilities, as you can see, it's really confident in this last class, and it is this last class. So the loss function here is lower. And this basically just teaches the model to classify correctly. And so next, the optimizer we're going to use is what is called stochastic gradient descent. And stochastic gradient descent is basically normal gradient descent, except we just work in batches. Traditionally, stochastic gradient descent worked on just doing one instance per loop. Basically, it's a batch size of one. Every single value was passed through and then updated. But that sort of stochastic gradient descent was basically very difficult to converge. So what we do instead is something called mini batch or just batch stochastic gradient descent, which is the standard basically. And so all you need to know is that we're going to be calling it as SGD. And that this is a pretty good example of what it looks like. Basically, we start out a loss, we update it, it kind of moves around, and then it falls in. So we're basically going to set these as a bunch of parameters. So anyone want to take a guess on how many epochs we should try and work with tonight? Keep it under 30. Anyone? I actually want to see if you want to give me a number. 20? Okay. Cool. So then let's do the learning rate. The learning rate, you're going to want to keep it less than 1. And like you would want it to be small. So anyone give me that? I actually want to see the sort of hyperparameters you would think. None? So you can give me a wild number, I don't care.
0.05.
0.05? Okay. And then the batch size, this one I'm going to give you, the batch size here will probably be 64. That's a good one. Then for the loss function, we're going to do neural net cross entropy loss. And it's literally as simple as calling it that. And then next for our optimizer, it's going to be optim.sgd. And then model.parameters. And this is basically going to grab all the weights and the biases, etc., from the model, and basically tell the optimizer, which has to update these parameters, hey, these are what they are. And then we're going to set LR to our rate. We're going to run these two cells. Let me turn on it. I'm sorry for scrolling. I have to make sure I write everything else. So I'm going to let this sit here and let you all write it. So cool. Now that we have our hyperparameters and our loss and an optimizer, now we're going to finally set up the final part of the process, which will just be our data loaders. And the data loaders are basically just going to control our batch sizes, and feed our data into the model. And this is easy to call, basically going to be data loader. Just like directly, and then for our training one, we're gonna feed in our training data. Our batch size will be batch size, like what we set up here. Then we're gonna do shuffle, and shuffle basically just going to mix up the data every time all the data is called through. And this is good because you kind of want to mix it up so the model won't. If you mix it up, then the gradients will always be different from one another after each training epoch, and it's just good practice. And then finally, num workers, and this is just the number of CPU cores you want to use. I'm going to close this. I'll minimize it. And then similar for the testing data, we're going to do test data, batch size, equals batch size, shuffle equals true, and num workers. And the reason why I'm setting the num workers is because Google Colab is dumb and slow and doesn't give you many CPUs. So you kind of actually have to use just do. And so we're gonna run that. Cool. And then finally, we now can finally get to the fun part. After all the work setting everything up, we can finally train the model after I can finish training. So for this, it's going to be simple. We're going to just basically call something in a loop a few number of times. So basically, we're going to do T, we're going to do epoch in range epochs. And this, and you know what format is. So we're going to first do print. We're going to do like, and now I'm just doing a format string of epoch I+1. Yeah, type. Well, yeah, it is I+1. And then we're gonna, this is basically just doing printing. Oh, see, this is what happens when I look at reference code. So, okay, now we fixed it, now it's epoch. And so the thing we're gonna do is we're first gonna call the train loop. So we have to do the training first before we do the testing. So we're gonna do train loop, train data loader. And we're gonna feed our same model and our loss function that we defined before, and then our optimizer. This will perform the training. And then once we finish the training for an epoch, we're going to call a test loop. We're going to do a test data loader. We're going to get a model, then our loss function. And then we're going to do that for a series of epoch, and we'll be done. So now that we have our training code implemented, we can just press run. And so now we're going to watch the magic happen of the function learning. And here's the not fun fact about training neural networks. They aren't fast, usually. This is, even with GPU, although given that there's good plug, this is not going to be super fast. So we're going to run this for 20 epochs. And as you can see, we're starting off great. We're starting off amazing. Actually, I'm going to go by. Nice one, thank you. So basically, as you can see here, every epoch, we're passing all of our training data through. And once we're done, you can see the loss function as it updates in real time. And then we're just going to check the accuracy on our testing data. And we do this at every epoch. And as you can see, as we iterate through the epochs, our accuracy for our testing data is actually getting better and better, and not so better, but then better. This is the magic of doing like something like stochastic gradient descent, that it kind of can shake it. but. So it's gonna take a minute, so does anyone have any questions so far while we wait for this to finish training?
I was Aaron, like, local variable, local variable correct from for time, I think it's that.
Can you check it? Appreciate it. This is what, if you guys become machine learning engineers, this will be what. Honestly, it will be like maybe like 15% of your job looks like. Most of your job will actually be, if you're there for machine learning 101, dealing with data, like getting the data ready to even feed into this. The other 30%, like a good 30% will be designing an architecture. And then this will be the fun part. I mean, I think the design is the fun part, but this will be the fun part where you can just sit back and relax. Like how many of you have seen that XKCD meme of compiling? How many of you have seen this meme before? You have? Yeah. Okay. How many of you know who XKCD is? I'm really hoping. Okay, y'all should learn about him. He's great and very, very funny. If you guys take computer science, he will constantly have good jokes for you. But this is the old traditional excuse for programmers, is that code compiling. If you do machine learning, is that your model's training. So, oh good, we're still not done. We're still taking forever. Has everyone else started running it or? Cool. So we're almost done. Last epic. You actually chose good with 20 because 20 is the one I already had internally. Thus, we're done. Cool. Let's see. Our testing error is a good 91.8%. Congratulations, you trained a really good model. So now we're going to just do the same thing as before. If you remember from our code up top where we just did some visualizations, we're going to do the same thing, but with the output. But we just have basically it's the same code as before. We just now have this little bit here, and I will explain this. Here, the only important thing you need to know is this torch.nograd. Whenever you're doing evaluation code, you want to call .nograd because you don't want to calculate the gradient because that just takes more time and takes more memory, and you're not going to use these gradients, so you don't want to calculate them. But let us just run. And we can now see our model making predictions. And based on this, it's pretty accurate. It's predicting 5, it's predicting 0, 4, it's doing well, right? Awesome. So, cool. We've run a model, we've trained it on a benchmark. Let's do something more fun. Let's try drawing our own numbers. So I have set up here, or let me rephrase it. I've stolen some code online that lets you draw in a Google Colab, and I edited it to let us run our own model. And if you see here, comment this out, because you don't actually have it there. But we're going to run this. And then we're going to run. So what number should I draw? Just shout out a number, I don't care. 7, let's do a 7. Finish. Why are they yelling at me? Oh. Let me do a correct cut to tensor. I did slight edits from what I have in here tonight, so we're going to be live bug fixing during the presentation. Again, 7 again. Fine, okay, I get it. And now, please. Forgive me for this. I'm gonna have to ask you all to put up with me. So what should we do? It should just be So because of tech, I'm basically just grabbing the first layer here. The forgive me if we go through the match fun process of live code editing when things change. So init code. Oh. We're gonna do a slight edit. We're gonna remove a little bit of code. As you all go through your years, especially once you start doing like senior design, you're going to hear this phrase. It's gonna fail, you're gonna hear the phrase and adage that everything will start falling apart during demo. This is true, okay. There we go. There we go, okay, now it's. Yeah, so, for some reason it said 3, let's try it. It was really confident, so. Oh yeah, by the way, if you wanna see the code I changed, basically there should be there's gonna be 2 lines right here. If you wanna scroll up and like edit this to have it work for yourself, there'll be 2 lines right here. Just delete them. They'll be between line width and button. It won't give you a white canvas in the background, but it will make everything else work, so. And then if you were following out to 3, so this will be the other half. No, clear out. So. And that. Let's try 4. I thought it was 7. No, that right. And so this is the magic neural network. You can do all the testing and all the validation. And then when you test it in the real world, it don't freaking work. Just don't. Shit. I'm gonna check something quick. Oh, it's fine. And then see the thing here. Correct? Oh, I think I know what's going on. Wait, no, it's fine. Well, at least it got it when I drew 2 correctly, it was fine. Yeah, anyway, but yeah, so this is just some fun code to play around with it. To finish. And as you can see, this is basically me outputting how probable it thinks each class is. So our model thinks this is 90% likely to be a 2. And it is a 2. Ooh. And then this is sort of like the model this is how it looks like when it's get inputted. Let's try a 0. And then there's a glitch. And it thinks it's a 7. It's really confident that it's a 7. Let's try a W. Who? Anyone think yet? What do you think this is gonna be? 3? More. Yeah, awesome. Anyone have any questions? Don't worry, we'll also be releasing the code after the workshop, so you can look at it yourself later. But
Can you explain what a gradient is? Like,
Yeah, sure, so. Basically, the gradient is the derivative. So, this is a great example. So if this is our cost function, let me. So if this is our cost function, like, and we're trying to reach here, the gradient is basically the slope of the line at that point.
Yeah.
And so what we're trying to do, we're going to use that gradient to tell us which direction we need to go in the loss function to improve our loss.
That's, I mean, calculators, I actually.
Yeah, okay, yeah. And this is exactly like basic calculus. This is actually very similar to Newton's method, if you're familiar with that. Newton's method is a way of, it's basically, it's very similar to this. You're basically going to take a point, see how long you are, and move down. And you're going to keep like incrementally improving your estimate until you get down to like an accurate answer. But, so that is technically the end of the workshop. Does anyone want to stick around and maybe play with trying to get an even better model than we have now? Or do you all want to go? All right. Then, thank you everyone in person and online for attending. I really appreciate it. If you have any questions, you can ask me now or just come up to me. As always, recording will be released, the code will be released, the slide will be released. I would really appreciate it if you fill out the questionnaire tonight, so we can know how we did. This is the first time I've ever covered like actually neural networks themselves, not like the traditional machine learning, so I really appreciate it. And please make sure you are available November 13th, where we will actually start getting into more complex topics, where we're going to be getting into computer vision and convolutional neural networks. And so this will be basically everything about images, everything about videos. Basically, if you like robots, you're gonna love computer vision. We're also learning learning, but you'll love computer vision. So if you want to, we're gonna be probably working with the same data we just worked with tonight. But please come. You'll actually get to see all about computer vision, which is one of my specialties. So thank you, everyone. I'm letting you go now. Be free. Thank you, Ida.